Greetings, folks. Just want to apologize here for some technical difficulties. Hopefully you've managed to find your way to our stream here. We had a little bit of technical difficulties getting everything to cooperate. Should be much better now. Should be able to hear us and see our slide deck here. And we're going to get started here in just a couple of minutes, so bear with us. Good evening, folks, and welcome to our webinar on scopes. We're going to talk about the Topdon Phoenix Max scope tonight, and this is going to be an introductory 101 level training. We do apologize for the technical difficulties that we experienced here just getting the webinar started. Ran into a couple of glitches, so hopefully you've managed to find your way over to the stream. And again, just do want to apologize for those glitches, and hopefully you've been able to sort it out and join us here on the webinar. So tonight we're going to talk a little bit about oscilloscopes, and specifically our Topdon Phoenix Max scope. So we're going to go into a few different things, and we'll give you kind of an overview of the class here, so you have kind of a feel for what we're going to cover, and basically you know, what we're going to run through here on the webinar. So at the end of this, you know, we're going to definitely take some questions. We've got a couple of folks with Topdon here who are working to coordinate that. If you do run into any issues As far as getting your questions to us, feel free to hit us up on the Facebook page and leave those messages there with respect to the scope, and we'll definitely watch those pages and get back with you if we do miss any of your questions in any of the stream chats. So again, do appreciate very much you joining us here. So for those of you who don't know me, I'm Haakan, and I am the national trainer here for Topdon. And again, we're going to cover our Phoenix Max with the oscilloscope. So this is a picture here of the Phoenix Max and our oscilloscope that comes with the tablet. So we're going to walk through just a lot of basics on the scope today and talk about some general principles of scoping various things. When you use a scope, how you use a scope, a lot of basic things like that. So hopefully this will make you more comfortable and familiar with the tool, but also just a little more comfortable with scopes as a whole. So here's some of the things that we're going to cover tonight. We're going to talk about, obviously, this is a 4-channel scope, so how do we leverage that and use all of the various channels simultaneously to our advantage, right? Obviously, we can look at up to 4 different signals simultaneously. Sometimes you're going to need all 4 channels, and sometimes you're only going to need 1 or 2. But it's nice to have up to 4 at your disposal when you are looking at a vehicle and trying to diagnose a problem. So we're going to talk a little bit about what a scope actually is. How does it actually work, right? What is it doing for you in terms of your diagnostic process? We're going to talk about some different accessories that you can purchase that will allow you to leverage your scope more effectively in your diagnostic process. Going to talk about how we get the waveform on the screen, right? That is probably the biggest challenge for most scope users when they're first starting out, is how do I get the waveform to look like what it's supposed to look like, in order so you can make an evaluation of whether or not that waveform is good or bad, acceptable or faulty, right? So we're going to cover that and try to get you some level of familiarity with how you get that waveform on the screen. We're also going to talk about just a little bit about what a good or a bad waveform looks like. We're not going to get into the nitty-gritty details of that. That's not really the goal of this webinar, right? We're not trying to get into the specific anatomy of every waveform on every system. There are books out there, which we're going to show you one of the books tonight. We're also going to talk about some different resources that you can access that will allow you to learn what is a good waveform, what is not, how to make diagnostic judgments on waveforms and things of that nature. So please keep that in mind. Again, we're not going to dive into the nitty-gritty on a bunch of different components or circuits. We're just going to give you some general principles, get you a little bit more comfortable with the scoping subject matter as a whole. We're also going to talk about how do we access a circuit, right? And that's important to remember because there are multiple different methods of connecting to a circuit. We need to understand what those methods bring to the table as far as value. We also need to understand what the drawbacks are of those methods, right? Because each of the methods that we can employ have specific utility given a certain situation. So we'll discuss those and talk about each of those in a little bit of depth just to help you understand what are the limitations when you make a specific choice about a method. What are the advantages? What are the drawbacks? You do need to know those when you are making those choices, because ultimately otherwise you could accidentally make an incorrect diagnostic conclusion. You could make an error in judgment on whether or not a component is faulty if you don't understand the limitations of your test setup. So again, very important to cover that, and we're going to go into that just a little bit as well. We're also going to talk about the practical diagnostic logic of using a scope, right? We need to understand when's the right time to use our scope. Also want to talk about what is it specifically? What tests are we going to do? And what kind of data is that going to yield for us in terms of our ability to diagnose a problem on a car? We want to understand what the value and the utility is and realize how we can make those evaluative decisions when we're working on a vehicle by using the data we collect with the scope. We're also going to talk about limitations of those tests. There are situations where the scope is not going to be able to get you what you want, or you might have to use it in conjunction with something like a scan tool. So just another thing to keep in mind. We're also going to talk about the basic user interface on the Phoenix Max scope. So we'll show you more or less the majority of the screens on the Phoenix Max scope, and we'll walk through each one of those screens and kind of give you a little bit of a feel for what each button on the screen does, when you might use it, things of that nature. Again, we're not going to dive into a super ton of depth with that, but we're going to get your feet wet a little bit and give you some level of familiarity and comfortability. We're also going to talk about a couple of go-to tests that I would highly recommend getting yourself comfortable with. I would also encourage you to take additional scope training, some of which Topdon plans to provide in a webinar format like this, and potentially at some large training conferences. Also going to do some live demonstration of a couple of different tests just to get you familiar with the operation of the scope, show you how to get the waveform on the screen and whatnot. So we'll walk through that as well. So now we're just going to talk briefly here about the overview of the scope itself. So the Phoenix Max scope, as a matter of fact, has 4 channels, as we talked about. We've got 200 volts of overvoltage protection per channel. Now, why does this matter? It's important to understand that the circuit that you're going to connect your scope to, you need to realize whether or not that voltage could possibly exceed that 200 volt threshold, because you can actually damage your scope if you happen to expose it to voltage that exceeds the protection level. Now, they're designed to not fail if you go over 200 volts, but that is not something you really want to test, right? As a general statement, you want to protect your tools and take good care of them. So again, make sure that you know what the circuit is going to be from a voltage perspective. If you're not sure, again, we're going to talk about some groups that you can post questions in and get some assistance from people who are more veteran users, and they can provide you some insight, helping you figure out whether or not that's a consideration you need to be concerned about. We'll also discuss attenuators, which can protect your scope specifically from overvoltage situations. This scope of ours also has a 50 million waveform buffer, so you can actually capture a large volume of waveforms. Essentially what we like to say, get a lot of time on the screen or capture a lot of waveforms for review or examination after you pause the scope. So that's obviously really helpful for diagnostics. We also have the ability to save and review waveforms after disconnecting from the vehicle, and you can actually save the waveforms in a couple of different ways. We will talk about that a little bit more in depth, just so you can have some familiarity about how you might save them or why you might save them one way versus another. We've also got the ability to do screenshots and screen record whenever we're working with the scope, and this is something that will help you catch glitches and review data better at the end of your process. So I definitely would highly recommend getting familiar with screen record and screenshots, which of course we are also going to cover during this webinar. So let's take a tour. Let's go through the Phoenix Max and look at some of the screens so you can get a little bit more comfortable with all of the different screens that there are and familiarize yourself with some of the features that you need to be aware of. Now, I'm actually going to switch to the screencast of the scope itself at the very moment, because I want to show you something you need to do before you use the scope on literally any vehicle. We're going to go into the menu button here, and we're going to go into, now pardon me, right here, under User Set. You see this section here where it says Factory Reset, Self-Adjust, Save Recovery. We're going to go to Self-Adjust. This is the first thing you need to do when you get your scope out of the box. You're going to plug in the USB cable, you're going to connect the scope to the Phoenix Max, and then you're going to go into this menu after the software boots, and you're going to click Self-Adjust. You should not have any other cables connected to the scope, just the USB. When you press Self-Adjust, the tool is going to go through an automatic zeroing and calibration process. So if you start to have issues with the scope, you have noise on signals, things aren't looking quite right, this is a process and a procedure you want to do. I do it periodically just to make sure everything is zeroed out correctly on the scope, and it's very important that you know how to do this. Again, this is the first thing I would do when you take your scope out of the box. If you have not done this process yet on your scope, I would highly recommend you take the time to do exactly that. So we're going to go ahead and we're going to switch back to the slide deck here. And now we're going to go through some screenshots. So on our first screenshot here, we have our voltage scale. So you're going to ask yourself, okay, what is a voltage scale, right? Well, in order to understand what a voltage scale is and what it does, we need to know what a scope physically does. A scope is mapping or drawing voltage over time. So on your vertical axis, that's voltage. On your horizontal axis, that's time. So essentially what the scope does is collect a lot of data points and then draw a line connecting those data points as it continuously collects data. So we see everything captured as lines, but the scope is physically capturing thousands of data points per second. Again, voltage over time. It's making voltage measurements rapidly at a much faster pace than a digital voltage, an ohm meter, or graphing DVOM, right? So that's what you need to know about a scope in terms of its basic functionality. So we need to be able to manipulate both our time scale and our voltage scale to properly get the waveform on the screen. So like I said, on the top right here with the yellow kind of box around it, that's where our voltage scale lives. We're going to show you a little bit more in depth in that, but we're going to go to the time scale next first. So now we've got the time scale here. So the time scale on the screen you can either manipulate with the two buttons to the left and right of that circle you see down at the bottom, or you can click on the numbers at the bottom there where we have the circle, and you can bring up this screen here that we see where we can physically see all of the different time scales all in one giant menu, if you will. And then you can select them individually if you want to click through it faster. Otherwise, you can just play with the buttons to the left and the right of the circle to go up and down in time scale. And you can visually observe what happens to the waveform as you do that, and you will see that as we do the demo of one of the waveforms to show you how we get a waveform on the screen, right? So now, going in a little more depth on the voltage scale channel. If you tap on the voltage scale channel where it shows, you see right here we've got channel 1, 200 milliamps in the top right. So if we click on that, channel 1, 200 milliamps, which I can show you with the mouse here, right up here in the top right, channel 1, 200 milliamps. If we click on that, it brings up this menu we now see on the left. So on this menu, we've got number 2 here. We're circled AC or DC coupling. So that's dependent on the circuit that you're going to analyze. Are we looking at a DC voltage sample, or are we looking at an AC voltage sample? And again, that's something you need to educate yourself a little bit more in order to understand what to select. Now, if you're not sure, most components on vehicles are generally going to be DC. There are a few that are AC, and there are certain tests you may perform that will require you to set it up for AC. Now, the other selection we have on number 3 here is the probe type. So we've got voltage, or VOL, and we've got current, CUR. So voltage is used for direct voltage measurements, right? So we're going to literally connect directly to the circuit and measure the voltage on the circuit directly. Current uses what we call a transducer, or an amp clamp. Now, the term transducer is generic in nature, and actually transducer refers to a device that converts something, whether we're talking about pressure or current flow or magnetic field, which is really what an amp clamp is, but it converts it to a voltage signal, right? Allows the scope to draw the waveform on the screen. So a transducer, again, is something that converts some other type of measurement to a voltage-related signal. So when we are doing voltage direct measurements, where we're physically connected to the circuit directly with a T-pin, piercing a wire, things of that nature, that's going to be voltage. When we're going to use something like an amp clamp, we're going to use current. Now, you can use voltage on an amp clamp as well, because the output of the amp clamp is still going to be voltage. However, the settings on current are going to modulate more specifically to accommodate specific amp clamps, right? So on number 4 here, we see scaling. So many amp clamps will put out a specific amount of voltage per millivolt or per milliamp of current that they measure, right? So the output is in volts, the input is how many milliamps it is measuring in current flow. So when it does that, there's a scaling factor. And in order to determine the scaling factor, most manufacturers will provide you with that scaling factor on your amp clamp. Now, if you don't know how to do that, here's an example you can use. If you have a small headlamp bulb or taillight bulb and you have a DVOM, you can power your small headlamp or taillamp bulb using your DVOM, set to amp mode, and run the bulb through your meter, measure the amperage, and then you can connect the amp clamp around the negative wire on the bulb. Then you can calibrate your amp clamp output on the scope to the known value that you have on the DVOM. So if the DVOM is showing 4 amps, you can go over to your scope, play around with your settings until you're seeing something that matches up, right? That's how you can determine what your amp clamp outputs if you have a known amperage to measure it against. So just an idea there if you're having any issues figuring out the conversion. Now, you might also go to Super Mario Diagnostics. He actually put out a very good video on exactly this, on how you determine the proper scaling and conversion rate for your amp clamp. So I would encourage you to go check that video out. Again, tons of resources on the internet for these kind of things. Don't be shy. There's so many things at your fingertips. Highly recommend checking it out. Pardon me for a moment here. I just got to take a drink. So now we're going to go number 5. You're asking, what is number 5, right? Number 5 is our filter. The filter is used to filter out extraneous noise. So when you are scoping a circuit, whether we're doing voltage or current, sometimes you will get noise contamination in the circuit. Now, some noise on the circuit is fairly normal in a lot of cases. You may scope a cam sensor circuit or a crank sensor circuit, and you may see something like a little tiny ignition waveform. Sometimes you will see that contaminating the signal. In many cases, that is completely normal. Now, if you turn on the low pass filter, many times it will kind of filter that out for you. Not always, but a lot of the times it will. So you can use the low pass filter to clean up your waveform just a little bit. And I would encourage you to play around with the filters a little bit, but suffice it to say, most of the time, the low pass filter is the only thing that you're really going to get into. Now, if you really want to know more about filters, again, there's lots of scope training out there that will cover this in more depth. And again, we'll do some webinars on a little bit more in-depth content on this subject in the future as well. So now we've got cursors. So in the top right here, basically you have horizontal and vertical cursors, which allow you to measure the amplitude of a waveform, the time duration of the waveform. So again, vertical cursors here, if we're looking at top to bottom, we are measuring our voltage or amperage, and our horizontal cursors, so that would actually be technically x-axis, as you see on the diagram here. The x-axis is going to be the measurement of time. So that would be something like, hey, I want to look at how long the injector is open for. So you could compare cylinder to cylinder, and you could see how long the injector is open for, which, if the injector is open longer on one cylinder, could be because the vehicle thinks that cylinder needs more fuel, right? So the cursors can help you measure things like that. Now, it also has, not really sure what the best way to say this is, but essentially like a mask for timing, to look at cylinder timing, event timing, and things of that nature. So essentially we can set up how many cylinders the engine has, and then also you're usually going to put in the angular measurement of 720. That's the most common. Again, there's lots and lots and lots of training on this specific subject and how to use this and leverage this. I would highly recommend you investigate that training and look into it. Brandon Steckler does a class about pressure transducers and things of that nature and covers this particular subject very much in depth. I would highly recommend. He teaches the class for CTI. He also teaches it independently as well. That would be a great class to get familiar with what the use of these rulers are. And I guess ruler is probably the best way to put it. So now we're going to go through the other basic menu options in the top left. So top left is the menu button. We're going to click on that menu button, and then we're going to get all these options just below it. So we got measure, we've got save, we've got display, we've got trigger, user set, and about, right? So we're going to go through and walk through each of these just a little bit. So measure, we have the opportunity or the capability to select which channel we want to measure something on, and then we can measure what specifically we want to capture, right? So in this particular case, I selected channel 1, which is the yellow, and I selected amplitude of the waveform, and then I selected channel 2, and I selected amplitude, and you can see that that's also the color mirrors here under amplitude. So the amplitude measurement highlighted there matches the color of the channel. So we can see channel 2, amplitude measurement, channel 1, amplitude measurement, right? So we can measure independent things on independent channels, which is nice, right? It's valuable so you can see what exactly is happening on a circuit, get empirical values that you can check against. Hey, if you have two components on a car, one's doing something normally and the other one's not, you could use these to measure and compare data, right? So a valuable tool. So now we're going to go to save. So under save, we've got a number of different options here for saving. Now these are not the only ways that you can save waveforms. It's also important to remember that when you're saving waveforms, excuse me, you are saving individual waveforms one at a time. Do you notice how we have the channels radio buttons right here? So you have to select which channel you're going to save the waveform from. It does not save them all simultaneously. So it is very important that you remember that, because otherwise, if you think you're saving, let's say you're doing a cam and a crank correlation, and you've got 2 cams and a crankshaft, if you do not go in and save each individual channel, you will not have all of the waveforms saved. So let's talk about a couple of things here. If we save it as a waveform, or WAV, that's going to save it to the tool, and the tool will allow you to recall it in that format. If you save it to a CSV, you can actually pull the CSV out from the tool if you connect it to USB, and you can graph it in Excel or Google Sheets. It will allow you to make a graph. Now, if you'd like to know how to do that, we could certainly do a webinar on that. Absolutely something I'd be happy to teach. Now, you can also name your file, and you can save them to reference waveform banks, 1, 2, 3, or 4. So you could map your cam and crank. You could say channel 1, save to R1. Channel 2, save to R2. Channel 3, save to R3. And you could do on so on and so forth. Then you have the ability to recall all of those waveforms simultaneously, which would allow you to see their synchronization or timing to each other, which is obviously crucial if we're trying to verify if an engine is in time. So, we're also going to talk about other methods of saving data. One of the other methods you can use to save data is to do a screenshot. So if we go down to this bottom right here, there's a little picture. It kind of looks like a mountain with a sun. That on the Phoenix Max lets you take a screenshot literally any time. So it doesn't matter whether you're in the scope or the scan tool. It's irrelevant. You can always do a screenshot on the Max by clicking that button. So again, that might be a situation where I would get a cam and crank waveform on the screen, stop by hitting this run button down here. We would hit run once and it would change to stop and it would show red. And then we could do a screenshot when we have the waveform on the screen in the way that we want, and then we just have a picture, right? You can't manipulate the data, but you have a known good picture right then and there, which is very easy for review. That's my personal favorite way of capturing the waveforms. The other thing you can do is you can turn on your screen record function. And if you turn on your screen record function, you can actually record the waveform and see a full video for as long as you leave the waveform or the screen recording function turned on. Obviously, it's a really valuable tool. It's great for scan data capture. It's great for scope capture. You always have that video, and the video can be exported off the tool by plugging it into USB, in which case you can review on your computer, you can save it to your Google Drive, you can put it in your shop management system, you can freeze frame the video and take a screenshot out of that. So a lot of value there on that front. So now we got display. Display I don't usually play around with, but you can manipulate the brightness of the scope. I don't really play around with any of the other stuff here. We can go into depth on these, but I don't see a lot of need to cover these right now. Trigger. So trigger is something you may end up using in the future. Essentially what this is for is getting the scope to grab something when it passes below or above a specific threshold. And we're talking about voltage here, or amperage. I don't frequently use triggers. There are a lot of videos out there explaining how to use a trigger effectively and when you might use them. Scanner Danner has a number of videos on this subject. I would strongly recommend checking out his channel. He does a great job of explaining when you would use a trigger, why you would use a trigger, but this is where triggers live in the software on the scope. So if you're trying to determine where they are and you want to use them, this is where you access them. I guess if you folks are really interested in triggers, we could do a webinar on that as well. Again, there's no limit to how many subjects we could do in depth on the scope, honestly. There's so many things it can do that obviously we're not going to cover them all tonight. So then we've got here user set. Depth is the one that you really want to pay attention to here. Depth is essentially the sampling rate. So how many times the scope is, if you will, capturing data points. So 50 times 10M is the highest sample rate. This is the sample rate I always select. It's just the way that I do things, right? I would recommend doing that. It's the highest depth of sampling. It's going to give you the most clarity of the image and the best data quality. So I would always leave it on this. I wouldn't even bother to leave it on auto or change it whatsoever. The other thing under user set, which we already talked about, was the self-adjust function. So remember, the self-adjust function if you have any issues with noise on any of your circuits, or the zeroing function when you go to turn on a channel doesn't look like a zero with nothing connected to it, do the self-adjust, and that will usually take care of any issues you're having there. So now we're just looking at recalling waveforms. So this is an example. In the top right here, we've got this button that we can look at that allows us to see our menus. So when we click on that, it actually brings up, we had the channels listed over on the far right before. Now we have reference waveform buttons we can pull up, right? So we have the ability to turn on up to 4 reference waveforms simultaneously and display them on the screen. So in this case, you see we've got reference bank 1 turned on. We can click right here to select a specific file. And if you name your files something specific, I would recommend, there's a character limit, so you can't put a whole lot of detail in here. I would recommend maybe coming up with a numbering system, like maybe your RO number, something along those lines. Something that will allow you to correlate it, maybe the last 6 of the VIN. Do something consistent here so that you know what it is that you're dealing with. So you have a good database that you're saving. Now again, if you save these as CSV files, you can pull them all off the tool and put them on a Google Drive or something along those lines for further review at a later time. We do have access to math channels and a couple other things here. We're not going to get into those tonight. Again, that's another function that requires some additional depth of training if we're going to get into it. So now you're asking yourself, does the scope have any pre-settings I can use to get things set up in advance? Make it easier on myself, right? The answer is yes. You do actually have the ability to pre-set up certain things in advance. There are automatic settings. So a lot of scopes have come out with this technology now, and obviously ours is no stranger to that game. So we do have a number of pre-settings that you can play around with. The automotive button down here on the bottom in the yellow square is how you access these pre-settings, and we'll show you kind of the gamut of pre-settings that are available on this scope. So under circuits, we've got 12-volt charging system, we've got alternator AC ripple, we've got 24-volt charging system, we have Ford smart alternator, we have 12-volt starting, 24-volt starting, and cranking current. The tool essentially shows you how to set up and probe that specific circuit when you click on it. So you can see over on the right here we have 12-volt charging. It says, hey, please connect channel 1 to the positive of the battery with a BNC banana. Connect channel 2 with a current probe. So we're basically measuring what is the voltage level at the battery, which is the voltage being fed back from the alternator, and what is the amperage coming into the battery from the alternator, right? So a fairly straightforward test, but if you need additional assistance setting these tests up, again, join some of these Facebook groups, reach out to support. We're happy to try and help you when we can, and we're more than glad to show you this. But we will walk through more of these tests in future webinars as well. There is also a multitude of other trainings out there teaching you how to set up a scope for all of these tests. So under sensors, we have a ton of different options here. So we've got ABS sensors, we've got accelerator pedal position sensors, we've got airflow meters, which would be a mass airflow sensor. We've got camshaft sensors, we got coolant temperature sensors, we got crankshaft sensors. Now we're on crankshaft sensor right now, and you can see that we actually have 3 different selections. We've got inductive with the engine running, and Hall effect. So if you're not sure what kind of sensor it is, do some reading. Take some additional classes. They can teach you how to identify what kind it is. It's very important that you learn these things because you need to know how to connect your scope correctly to the vehicle. Understanding system operation and, more specifically, component operation is very important to your ability to use your scope effectively and interpret the data that your scope provides to you. Actuators. We have a number of different actuators available here for pre-setup. We've got a carbon canister solenoid, we've got diesel glow plugs, EGR solenoid valve, fuel pump, idle speed controller, IAC. We've got injectors. Now the injectors that you see here, those are going to likely be pre-setup for manifold injection, they kind of died out a little bit when GDI or gasoline direct injection started to come along. And now they're kind of coming back because more and more manufacturers are doing dual injection where they have manifold injection and also direct injection. Ford has it, Toyota has it, I'm sure there are some other manufacturers using it. They're doing that mostly to avoid, well, not mostly, but partially to avoid issues with carbon-on valves, better atomization of fuel at various points of load status of the engine. They will modulate and use different injector sets depending on what the conditions of the running is for the vehicle. So again, lots more training out there on that if you want to get more educated about that. But I do believe that the settings on the scope are pre-set up for just regular manifold injection. Now, it's important to remember that, again, our scope is limited to 200 volts of overvoltage protection. So if you're going to do something like a piezo injector on a direct injected vehicle or a diesel vehicle, some of those, the voltage can approach or exceed 200 volts. Not for usually typically long periods of time necessarily, but instantaneously, which could still be enough to damage the tool. So we'll cover what you use in those situations to protect your tool from those kind of issues, right? You can also look at pressure regulators, quantity control valve, throttle body, so we're looking at the throttle motor, variable speed cooling fans, and variable valve timing solenoids as well. So a number of different actuators that are available for pre-setup guide. Now, we've also got ignition. So on ignition, you can see when we click on ignition primary, it says, hey, what do you want to look at? You want to look at voltage, you want to look at current, you want to look at voltage and current, you want to look at the trigger signal. What is it that we're looking at for primary ignition? Now, primary ignition is we are going to physically tap into the connector at the coil. We are not just clamping on a transducer or an amp clamp or an inductive probe. We are physically connecting to the circuit if we are going to measure primary ignition voltage directly. This is another situation where you want to use an attenuator, which again, we're going to show you what an attenuator looks like. And again, there's a couple of situations you want to keep in your back pocket where you need to use it. That's not necessarily all encompassing. You need to do further education about systems to determine what situations you should be using one. So, definitely don't need to use it all the time, but there are many situations where you do. Now, if you're concerned about your scope and you want to protect it, you could use a DVOM that has a higher voltage protection, or you could get a cheap DVOM you don't care about, and you could back probe that circuit with your DVOM and find out what the maximum voltage is. Most DVOMs have min-max voltage capture, so you could watch that and likely see what the maximum voltage of the circuit is. Now again, that's limiting because DVOMs don't sample very quickly, so there's always a risk that it might not catch a overvoltage condition on DVOM. But that is an option that you could at least entertain to try and protect yourself from overvoltage situations. Now we can also look at secondary or primary and secondary for ignition. So we have a lot of different options here. Now we have communication networks. So we've got CAN bus, LIN bus, FlexRay bus, and also K-line. K-line and LIN are smaller single wire networks. FlexRay and CAN are both two-wire networks. And of course, the speed of the FlexRay networks are much faster than CAN networks. FlexRay is starting to penetrate into more and more vehicles and more systems because more and more vehicles are even greater connectivity than we've seen in previous generations, right? So just a lot of things to keep in mind when we're scoping these. We're going to do a little bit of CAN network tonight, show you how to get a waveform on the screen. We're not going to get into anything other than that tonight, but we are going to demonstrate a CAN network waveform just so you can get a little bit of a feel for that. Combination tests. This gives us an option to look at a couple of common things at the same time. So crank and camshaft, certainly very common, something you would most certainly end up looking at on a regular basis on a lot of modern vehicles. More and more vehicles that have timing chains are stretching timing chains and having timing issues, which of course results in timing fault codes in most cases. Not always. You can have a timing problem and not have any timing relating faults. So it is very important that you remember that. Now, we've also got crankshaft and primary ignition if we want to look at that. We can also look at primary ignition and injector volume, or voltage, excuse me, not volume. So if we want to look at that, we can kind of look at the correlation between the two. Primary ignition and injector voltage can allow us to see things like the cylinder charge, right? Is the charge lean? Is the charge rich? What do we have as far as fuel delivery, air delivery? What is the ratio and the mixture looking like? Is it igniting properly? Do we have an excess of fuel or a deficiency of fuel? Crank and cam, along with injector voltage and secondary ignition. So again, these are all just pre-settings, But of course, you can come up with your own tests as well. These are just the guided functions that the scope has pre-built into the software. So now, here's another feature that I want you to keep in mind, zoom. So how do we use zoom effectively? Zoom is a tremendous tool. So when you're using the Topdon scope, what I always recommend doing, if you're doing any scoping whatsoever, I always recommend zooming out, right? So we're going to zoom out and put a longer time base, like 100 milliseconds or more than that. What you want to do specifically is going to vary by what component you're testing, how much information you're trying to get on the scope screen. But essentially, you can maximize that particular value on the scope and say, hey, I'm going to put 5 seconds on the screen or 10 seconds on the screen. And then you can hit that button down on the bottom right here where it says, now it shows stop before it showed run. But you hit run and then it changes to stop. So right now it's frozen and it's stopped. We've purposefully stopped it from continuing to collect data. And then we click on the zoom button. And then the zoom button gives us a little window here that we can drag back and forth left and right. And we'll demonstrate this live on the car too. And then down here we have 2 time scales. So the top time scale is the time scale we see up here in the window. The bottom time scale is our zoomed in tiny little, you see the black darker section here, that's 10 milliseconds of time inside that black section. Gray is 100 milliseconds on the screen effectively. So what we're dealing with here is the ability to zoom in and review the data, and it will allow us to capture, so if we capture, let's say, 20 of these humps, which this is a purge valve, but if we capture 20 of these humps, and maybe we have a glitch 1 every 20. Well, if we get 20 on the screen and we can see 20 of them, then we can say, hey, look, that one doesn't look the same as the other ones. That's kind of strange. Maybe we've got an intermittently sticking purge valve. Then we could freeze it by hitting stop, or run, as it starts with. Then we can go up to zoom, and we can drag the window back and forth left and right to review the waveform and determine what's different about the one where it sticks. So we could zoom in and see the specific waveform that we think is maybe a little different or questionable, right? So zoom is a very, very valuable tool. Definitely one you want to get comfortable and familiar with right away. Here's another example of zoom, right? So we could see here on the top, look, we have a ton of these toggles, high-low toggles, and maybe this might be zoomed out a little bit too much for us to see a whole lot of detail. But if you happen to pick something out of here and you go, that looks a little suspicious, we could use zoom again, and this time we got 500 milliseconds up on top on the screen, and on the bottom, 50 milliseconds of time. So it's a pretty fast signal. And here's one more. So here's one, this looks like a crankshaft signal, right? We have a bunch of toggles, and then we have a big missing tooth section right here. So in this particular case, let's say we had a crankshaft position sensor fault code. We could do this, and we could essentially freeze the screen multiple times, or we could take a longer time sampling than 500 milliseconds, and we could spool through the entire revolution of the crankshaft, look at every individual tooth, and determine if there's a problem with one of the teeth. Now, you ask yourself, what would a problem look like? Well, if we've got a problem with a tooth, we could have an issue where the waveform doesn't reach the same amplitude. So if we look at this here, we've got very symmetrical peaks, right? We're at, what, 5.5-ish volts roughly? 5.6 volts, somewhere in there. Each time it switches high, it's about 5.5. Each time it switches low, it looks like it's about 690 millivolts, right? So we have the ability to review this and find out, as we spool through the entire signal of the crankshaft through one whole revolution, we can pick out if there's a tooth that's damaged. The amplitude of the signal will be different. It could be higher, it could be lower. It all depends on what problem we have. It could be lower in some spots, higher in others, but if we see that, then we know that we need to go inside with like a borescope, remove the crankshaft sensor, and slowly turn the engine and use a borescope to look inside to visually inspect the tone wheel or the teeth to determine what is going on, right? We could have a piece of ferromagnetic material on the tone wheel. We could have a bent tone wheel. We could have any number of different things. But if we review the signal in depth, we can see what's going on and why there might be a sensor fault. So now we're going to talk a little bit about accessories, right? I'm going to go over just a bit here, explain some of the accessories that exist that will allow you to leverage your scope more effectively, right? Now, the beauty of the Topdon scope is that it is a standard BNC style connection. So the great part about that is you have access to a ton of different scope accessories. Most scope accessories out there are available in a BNC format or in a BNC adapter. So you can use banana. So many of the scope accessories for like Snap-on come with banana jacks. You can buy a banana to BNC adapter, which means if you already have accessories that are banana jacks, no big deal. Buy a couple of banana to BNC adapters. Now you can use your accessories with your Topdon Phoenix Max scope as well. So we're going to show you a few slides of some accessories, and then we're going to show you them live on the camera. Because I don't know about you, but I kind of like to see things with my own two eyes. So another tool that's really valuable, fuse and relay current taps. So what can you do with these that you can't do other ways? You can stick these into a fuse cavity, and you can view what's happening on the circuit of that fuse. So in many situations, for instance, vehicles will have a dedicated fuse for fuel injectors or for ignition coils. You can substitute this connector on the bottom left here, put that in place of the fuse, and then you can plug your fuse into the body, which we'll demonstrate this live on the camera. And then you can either tap into the voltage to see what's happening voltage-wise on the circuit, and or you can clamp around the wire with your amp clamp and view what the current flow is on that circuit. So a lot of ability to evaluate the circuit with more depth and a little bit more quality. Now, again, that's going to be somewhat dependent on how many different things live or are operated off of that same fuse. More and more vehicles have a larger volume of fuses, so there's a better chance that circuits will be isolated into individual fuses. However, it's important to keep in mind that there are situations where too many things are found on the same fuse, and so this becomes not a viable option. Similar thing can be said for the relay taps. They have similar functionality available. They make these with a little loop on the top similar to these fuse taps. So very easy to get a hold of and super valuable. So now we talk about ignition. We talked about ignition probes. We said primary and secondary. Primary, we're going to physically go and access the connector directly, and we're going to plug in with our probe directly. So voltage directly, right? There's also secondary ignition probes. There's a number of different forms of secondary ignition probes. On the bottom left here, we have an inductive style clamp. These clamp on to spark plug wires if you have a vehicle with wires, like the vehicle we're going to demonstrate tonight. Or if you remove the coil, you can place this wire in between the coil and the plug and clamp onto that with that style connector. However, it's important to remember, if you have a coil-related problem and you happen to disturb that circuit by dismounting and removing the coil and placing this intermediate wire in between, you may run into issues where you could accidentally temporarily fix or resolve a concern without really realizing you've inadvertently resolved it or fixed it, right? So just a pitfall to be aware of by using that intermediate piece there. It is possible to use it, and if you're sure it's not a coil-specific problem, like it's not seating or it's cracked or something along those lines, then you can certainly employ this and it does work. Now on the bottom here in the yellow, that is an inductive probe that can be clamped onto the coil, which you can use while driving as well as at idle, and you don't have to physically hold it onto the coil. In the bottom right, we have a coil probe wand. Now, there is something to keep in mind with a lot of these ignition probes. So with the inductive style like this, where it's a transducer and it mounts on the top of the coil, either the wand or this one in the middle, both of those can be limited if the coil is magnetically shielded. So more and more vehicles use magnetically shielded coils. If you place one of these two tools on the coil and you don't see a secondary ignition waveform, the odds are the coil is shielded excessively and you may not be able to see what is happening in the secondary ignition. In those cases, then you have to look at primary ignition. So we're going to show you a couple other things here so we can see probing tools, right? We need to connect to circuits in a variety of ways. Now, whether we're looking at primary ignition or we're looking at a purge valve or we're doing any number of any things in between, there are multiple means of connection available to us. We're going to go into depth a little more on this a little later here, but we've got T-pins, which of course you can basically gently and carefully slide these in the back of the connector and make contact with the metal pins that are physically carrying the signal or the current, and then clamp onto them with the spring hook, which you see directly below, right? That's my personal favorite method. You buy the T-pins, you can get those at like Michael's or a craft store. Excuse me. And then you can get these spring hooks from a number of different retailers, including Picoscope makes them. AES Wave is another place. You can buy a ton of these accessories, and they're very good at carrying this stuff. And basically, you can clamp onto these with the spring hook. They also make these back probe style where it's an all-in-one. You physically just plug your wire directly into the back probe, and you can replace the little T-pins. I've used those before, too. Those work fine. You also have piercing probes like this, where you can physically pierce the wire. A lot of people are not big fans of piercing. We'll talk about the feature or the drawbacks and the benefits to doing each of these different methods. You also have breakout harness kits like this. The breakout harness kits are a great value. You can isolate specific circuits, divorce them from other circuits. You can, it's a very good way to not damage a circuit or a connector. Back probing can cause damage to connectors, so you do have to be concerned about that. You've also got small clamps like this to clamp onto various conductors, as well as the bigger alligator style as well. And then on the top right here, we have a kit that you can get. This one does happen to be from AES Wave, where it comes from, or it has a number of different style of connectors. So you've got just a boatload of different breakout leads. You've got some of the fuse taps. You've got some of the little alligator clips. You've got some additional jumper leads you can use. Really covers a large amount of different types of accessories that you could use with your scope. So really a good option. Definitely encourage you to examine something like that. So, and then the other thing that we have, pressure transducers and pulse sensors. We're not going to demo these on this video. We will do a demo of these in the future and talk about some of the use of this tool. Obviously, Pico makes a transducer. It is compatible with the Topdon scope, of course, because it's a BNC connection, so no problem there. Otherwise, there's the one on the left is one that I found on the internet that is pretty affordable. Actually very affordable. We may potentially offer a transducer like this in the future, Topdon may. And then we've also got a pressure pulse sensor. So the pressure pulse sensor is what we like to call a delta sensor. So it's looking at change. They work a little bit differently from the pressure transducer. Pressure transducers can measure more in an absolute sense. I guess that'd be the right way maybe potentially to describe it, but different functions, let's just say. We can go into a little more depth on that in a webinar in the future, but essentially that's what we're dealing with. Is they work a little bit differently, both have value. Pulse sensors are generally used in many situations to look at exhaust or intake vacuum or pressure pulse captures to see what's physically happening, right? Again, we're looking for symmetry. So if we have symmetrical pulses across the board, that means that the cylinders are all breathing air in a similar fashion, right? Whether we're checking the intake side from the intake manifold or the output side, which would be the exhaust pipe, right? We're looking for symmetry. Symmetry indicates the cylinders are functioning symmetrically, which is ideally what you want from an engine, right? So now we're going to look at a live look at a few accessories. So you get to see my face on camera now. So we're going to transition over there. And if you give me just a moment here, we will switch over to the camera. So now we're going to demonstrate just a couple of the different scope accessories so you can kind of see them with your own eyes. I like to see things with my own eyes. I find that get a little bit better feel for what the product really is and how it functions for me. So the first thing we'll look at here is breakout leads. So this is another example of breakout leads. Basically what we've got here is we've got a number of different automotive connectors in various sizes, and they sell kits like this that come with all sorts of different sizes of connectors, so you can slide them in substitution for whatever component it might be, and you'd be able to check and see what's happening on the circuit, right? So you can plug your probes from your scope directly into this end. So that's really nice because it helps you avoid damaging connectors. Always recommend getting these breakout leads. Now it is important to remember, more and more modern vehicles, when you disconnect a component from the end of the connector, so let's say we have a purge valve, we disconnect it from one end where the component end is, and we pin in to see what our voltage looks like, you want to be careful. Sometimes modern control units will kill the circuit if they don't see a load or a component plugged in. So that is important to remember. So I would highly recommend purchasing a number of resistors, like a box full of resistors. because if you have a box full of resistors, you can stick the box full of resistors across, well, not the box, but individual resistors that are of the correct resistance or similar resistance to the component, and then you can plug that resistor into the connector instead, and the computer will still tell you or send the voltage out, which allows you to verify if the computer is actually working, right? So another pitfall you want to keep in mind when you are disconnecting and pinning in with a test harness like this. Because again, the computer could kill the circuit and lead you to believe, I don't have any voltage there. Computer must be bad. Well, be careful. You might be wrong about that. So now, these are a couple of the fuse breakouts. So these are one of my personal favorites. Again, it's got a little light on it here, if you can see that. The little light actually indicates when the circuit is lit up, when it's live. You put your fuse inside this side here. Basically just take it out of the cavity, stick it in here, then stick this in the cavity where the fuse was. Then you can tap the voltage right there, and you can clamp your amp clamp around here so that you can monitor both current and voltage on the circuit. They make them for almost every type of automotive fuse, and you can buy most of them in kits. And I got mine from Wave, although I'm sure there's plenty of other suppliers out there that do offer these. So just again, another tool that really allows you to examine a circuit in more depth and clarity without having to disconnect connectors a bunch or poke wires or back probe or anything else. If you can go right to the fuse block and look at the circuit there, it's definitely a nice advantage, right? So now we've got a couple other accessories we'll show you here. So there's a number of different style of amp clamps as we showed in the pictures. Many of the BNC styles, if not all of them, typically have a zeroing button like this. So when you first connect the clamp, you're going to hit your 0 button after you switch it on to make sure that the voltage output is zeroed. And then you have scaling here. So again, we can see the scaling setup. And again, Super Mario Diagnostics on YouTube does a great video on how to understand what this is and how it works. So most amp clamps of BNC nature will be like this. Again, we've got, that was a low amp probe, so the range on that one was, I want to say, I've forgotten now, I think that one goes up to 60 amps. So it has a low amp setting and a high amp setting. Then we've got a high amp clamp like this, which only has one setting. So this would be like something for looking at starter current, or if you have any other particular loads on a vehicle that draw a lot of amperage, this would be the clamp you would use. This one, again, I ordered this one from AES Wave, and you can get custom harness, which is really nice. Really helpful from that standpoint. That way you can get as long of a cord as you want, because some of the clamps don't come with a real long cord. Scope is also completely compatible with the Pico BNC, standard BNC. So Pico makes a lot of really nice quality accessories. I've used many of their scope accessories, and the quality is just great. So again, I highly recommend. This one has a dial style 0, so you'll see some of them have a dial style 0, some of them have a push button 0. So get familiar with what your particular amp clamp uses, and make sure you understand how to zero it out correctly. When you connect it to the scope, again, if it's not connected to any circuit whatsoever, the goal is it should be at 0, right? There shouldn't be any voltage output from the amp clamp if it's connected to nothing, right? So now a review, we can see, got a couple of the inductive ignition probes. These are what they call the ECOP. So those come from ATS, and those are essentially clamp right onto the coil so that we can see what the secondary ignition waveform is. Again, that's assuming the coil is not insulated significantly against magnetics. So if it is, you will not be able to see the waveform with this style of probe. Now, this is a pulse sensor. So you can buy pulse sensors. There's a number of guys who make them. Jarhead Diagnostics, Cody's AutoMD, he makes them, and numerous other guys. But the pulse sensors are all pretty similar in function. Essentially what it is we have a diaphragm inside the sensor here, and it outputs a voltage based on the distortion of the diaphragm, right? So the diaphragm gets distorted whether it's going this direction or this direction, whether it's vacuum or pressure, and then causes a voltage output to be induced through here, which goes to your scope. So these are not overly expensive if you buy the ones that are made by some of the diagnostic specialist guys. Obviously the Pico branded one or the First Look one also works with our scope. Any of those are functional. They all do the same thing. They're all very, very effective tools. Now, I don't have a pressure transducer like the WPS 500 or the other one we showed to demonstrate, unfortunately, with me today. This is that intermediate lead that we saw that was specifically for putting between the coil and the plug. Again, I would discourage using this in most cases. unless you absolutely need to, because again, if we're disturbing the circuit, it is possible that we could accidentally introduce other variables, right? And anytime we're trying to diagnose a problem, we want to keep the variables as minimal as possible. Oh, another shop touched the vehicle first, or another shop has installed 5 other components. Now our diagnosis has been complicated drastically. So just something to keep in mind there when we're dealing with that. So then I want to talk about one other thing here, and this is a book I would highly recommend. When you are getting familiar with scoping, the biggest thing you're going to go and find that you're challenged with is, how do I get the waveform on the screen? What is the waveform supposed to look like? This book is so helpful. I first started out and used this and got very comfortable with scoping much faster by having this. Now, is this a Bible to live and die by? No. This is a generic overview of what waveforms will look like for a lot of specific components. It doesn't have every component. It's not going to cover every base. You're going to run into situations where you're going to still need help from someone else, or you're going to need to take a class to have a deeper understanding. However, if we look in here, there are a number of different things that you can look at where this book will help you greatly in determining what does the waveform look like and what is the anatomy, if you will, of the waveform. So I was stupid and did not bookmark it, but we'll show you here if I can get this to look good on the screen. So we can look at, here he's got a picture of a fuel injector, and Graham actually gives you the anatomy of the waveform. So we can physically see what are the different elements of the waveform and what does the waveform generally look like. I think this is tremendously valuable because as a beginner, you don't know what the waveform's supposed to look like. So when you're pressing buttons and trying to get the waveform on the screen, if you don't know what it's supposed to look like, how do you know if you got the waveform on the screen, right? You don't. So this book I found to be very useful. I'll see if I can get to the ignition section. I always forget what page that is on here. Let's see here. So actuators, ignition, 131. All right, so I just want to show you an ignition waveform so you can see what the waveform looks like. And he does cover secondary and primary ignition. So here's an ignition primary waveform on this page. Hopefully you can see that relatively well. And then we've got a secondary ignition waveform, which will go a little bit farther here. Okay, so that's primary, primary, primary. Secondary, there we go. So here's a secondary waveform. So you can see the approximation of what that looks like. Now we're going to actually look at a secondary ignition waveform on the vehicle. And this should really make it a little bit easier for you to get a feel for, hey, that's what the known good or the general waveform looks like. And then we're going to look at what it really looks like in real life. And of course, we are going to scope a healthy vehicle that doesn't have any problems currently. No fault codes, no confirmed misfires, etc. Right? So just a couple things to keep in mind. There is one other book I would recommend. If you're getting more comfortable with electronic systems, I would strongly recommend buying this book. This is a very simple and straightforward book that teaches you a lot of fundamental or foundational, as I like to call them, electrical principles. I would also encourage you to take every electrical class you can find, because the more electrical classes you take, the better your understanding will get, and the more you understand electricity, the easier it's going to get for you to use your scope effectively, and the more you're going to understand the value it provides. Now, the scope is one of the most powerful tools in the automotive world, and it's becoming more and more vital every day you work on modern vehicles, because the more and more modern vehicles become computerized and we have more and more control modules and sensors, everything is monitored with a sensor, controlled by a computer. That means that when the computer asks for something to happen, it wants to confirm that it happened, so it will use a sensor, or it will monitor a voltage feedback, or something of that nature. You have to learn to understand what's happening on these systems, and the only way to confirm that they're physically happening with the speed that the computer sees it happen is a scope. You can certainly see what's happening with a lot of scan tool data, but there's a lot of lag on scan tool data compared to real life, right? Real life, scope is right now. Scan tool data, many times you can catch glitches with it, right? It's usually fast enough to help us on a lot of diagnostics, but not always. Sometimes you need that scope because it's so much faster. It can show you what's happening right now, not delayed, not, hey, I'm sampling data and there's a little bit of a lag. No, scopes are right now, show you what the computer sees. And you need to know what the computer sees to understand what the fault cause is in many situations. Okay, so we're going to go back over to our slideshow now. So we're going to talk briefly about accessing circuits. So when we're accessing circuits, there's a couple of different ways that we can access a circuit. We can back probe a connector. Which end of the system are we going to back probe? In many situations, it's very advantageous to back probe at the control unit end. Now, why do we say this? If you can access the control unit end and back probe it there, you are seeing exactly what the computer is seeing. So what is that telling us? Let's say we have a cam sensor fault. If we have a cam sensor fault and we back probe at the computer, we can see exactly what the computer sees. If it's a wiring problem or a sensor problem, the computer is going to see that. If we probe it down at the sensor end, there could conceivably be a good output of signal from the sensor at the sensor end, and if the signal wire is damaged, maybe the signal isn't getting all the way back to the computer. So you need to understand there are some issues with that, right? So we need to remember sometimes you absolutely have to get to the computer end of the circuit to verify what's really going on. And maybe you even want to probe both. Maybe you want to put one channel on your scope at the computer back probed and one channel of your scope at the component end back probed. So you can see, is what's happening at one end the same as what's happening at the other end? Again, the scope gives you the capabilities to see what's happening on a circuit in multiple locations. So let's even take it further, right? What if there's an intermediate junction connector between the component and the computer? Couldn't you use 3 channels of your scope? Say, hey, I'm going to connect at the component end, at the intermediate junction connector, and at the computer. Now what are we doing? Now we are isolating if there's a break or a damaged wire, we can determine where the break is in the harness. Or at minimum, cut that amount of harness that we need to examine down by a substantial amount. Now, if you're suspicious of a wiring harness problem, the other thing you can do that a lot of people forget about, and this isn't really a scope-specific tip, but you can run a jumper harness. And when I say jumper harness, I'm talking about backpinning directly at the control unit, whatever control unit we're talking about, and running a jumper wire directly to the component end and backpinning that. Why? Because we're bypassing the factory wiring harness. If we bypass the entire factory wiring harness, what do we know? Wiring and connection is no longer the problem. We're eliminating a whole heck of a lot. And that is infinitely faster than spooling through a bunch of wire that's routed inside the car somewhere trying to figure out where the break is, right? So just a helpful tip, not scope specific, but something that I want you to keep in mind when you're working on vehicles. Now, piercing a wire. There is a lot of debate over this subject, discussion over this subject. The harsh reality here is there are times that, especially if you're a technician who's being paid on flat rate, and I'm not blind, I know that there are still technicians stuck on that pay plan. I'm not personally a fan of that. However, there are still shops that pay on that pay plan. When you are a flat rate technician, it may be absolutely inefficient to go and access the computer or the component end of the circuit, or it might require a substantial amount of disassembly. Now, if your shop has great communication with your customers and you can sell the additional time required to engineer the proper testing method by back probing ideally, great. If you're working in a situation where that is just fundamentally not possible, or there's no way that you're going to be able to do it, piercing a wire is an option that's still on your table, right? In many situations, it's not ideal. It's much more of a problem in places where corrosion happens. The reason being is anytime you open the insulation on the harness, you do introduce the exposure to the elements, right? So that means we can have a problem where moisture can get inside the wiring harness and corrosion can form inside the wiring harness. And it can also wick other substances, oil, coolant, etc. Once the insulation is compromised, that can cause additional problems. So, if you're going to pierce a wire, we need to make sure we are completely sealing that back up. Some people will use substances like nail polish, there's liquid tape, new skin, which is a liquid skin substitute type of thing. There's any number of different chemicals that you can use to seal it. I would always say seal it with a chemical and then tape it back up with high quality, probably 3M branded electrical tape that's really good, right? That's the ideal thing. If you're going to go in and poke things, you need to make sure you restore the harness to a protected state where there's almost no chance of anything getting back into the harness, right? You don't want to cause a problem to the customer's vehicle as a result of a test you performed. They're not going to like it, and you're going to feel stupid. So the other option we have on the table is obviously the breakout leads, which we showed on the video, right? So we got the fuse taps. If that's feasible, if that works, we do that. Sometimes we could break out at the connector at the component end, put in a branch chain harness where we have a splitter, for instance. So some of those terminal probes that I showed you, you could get a Y splitter. So you could connect the component and have the component connected and also have a breakout where your scope can connect in a Y connection, right? So a number of different options there if you would like to be able to see what's happening on a circuit, right? So again, there's benefits and there's drawbacks. Now back probing is one other thing that I don't think I mentioned, but it is crucial to remember when you are back probing that you are gentle and careful, because when you push a T-pin or a back probe into a connector, you can accidentally bend a pin on that connector and cause a contact issue. So you always want to be very gentle and careful. Only push it in as far as you have to get a signal connected. So if you're connecting to a circuit via back probe, it's a good idea to have your scope running while you're doing it, right? Because then you can see live if you are properly touching the wire. Now, there's always a possibility that you won't be able to get good connection using a back probe, which again is why we do have piercing in our back pocket if necessary. So here's an opportunity here where we're just going to look at a little bit of a case. We're not going to get into like a case study or anything too exciting, but this is just an example I want to show you. So when you are talking about connecting to a circuit, you're going to have to use an adaptive strategy. What works on one vehicle may not work the same on another vehicle. In this particular case, this is a Ford. Let's say we wanted to look at the ignition coils and see how much amperage they are drawing, right? We want to find out. Amperage is a reflection of effort, if you will. So how hard are the coils working to ignite the fuel-air mixture, right? Well, we can look at all of them simultaneously because we have a fuse that's dedicated to the coils right here. So we can insert one of those jumper leads and we can physically monitor the current on every single one of the coils at the same time. We can also use primary or secondary ignition to synchronize to any one of these specific coils and then use a firing order diagram to determine which one of our amperage humps, if you will, which we'll show you a waveform in a moment here, is a specific given cylinder. So here is a waveform from exactly that. This is actually off of a Ford. So this particular Ford had 2 coils that were faulty and several fouled spark plugs. And you can possibly guess which 2 cylinders they were on. Now, how do you know which 2 cylinders the issue exists on? Well, number one, usually we would hope that the PCM or ECM would flag fault codes for misfires, right? And on a lot of vehicles, you'd be correct. Not all vehicles will flag them correctly, though. Sometimes we get incorrect cylinders flagged. Sometimes the computer fails to flag any cylinder. So we need to keep that in mind that that is a pitfall. However, in this particular case, we synchronized to a specific coil, and I don't recall which one it was at this point in time. However, we could see that the lower amplitude of the signal and amperage drawn on this particular coil, and that's the top waveform here, so the reddish, on that we have a lower amplitude here and a lower amplitude here. Now people always ask, what is good versus bad? I always tell people a good rule of thumb to live by, and I wouldn't say this is a universal or golden rule, but a pretty reliable rule. If you have a symptom on a cylinder, like this one, which is why we synchronize to this cylinder, and you have a 10% deviation, and so we're talking about, let's take all the coils that are healthy, and we'll add up and see, okay, what amperage draw do they have? Let's take 4 healthy-ish looking coils, let's look at their amperage draw, and then let's add all 4 up and divide and determine what the average amperage is, okay? So we can do that. So let's say the average amperage, and I can't read the scale on here because it's too small on my screen, but let's say the average amperage was 7, okay? Well, if we have an amperage deviation of 2 greater amps or 2 lesser amps on a given coil, doesn't that tell us that there's probably a problem? Especially if that correlates with a cylinder that's misfiring. Now this particular vehicle had 2 fouled plugs on this cylinder here and this cylinder here, and it's drawing less amperage. which means what do we got? So it's either drawing less amperage because the cylinder is much richer because it's not able to ignite it, which could be because the cylinder is rich because it's not igniting it, so chicken or the egg, if you will, or we've got a problem with the ignition coil's ability to ignite that fuel air mixture. The fuel charge may be correct, but the ignition coil is not able to properly ignite it, which is what the case was here. So we pulled it out, the plugs were fouled, and we put 2 new coils in this vehicle, and afterwards I didn't put it in the slideshow, but all of the captures were much closer together. We're talking like 1%, 2% deviation, very, very close, maybe 5% at the very most, even in the worst case scenario. So again, we're looking at we got to be adaptive in our approach, right? We got to get some general rules of thumb. 10% deviation that correlates with a symptom we can feel or observe or a fault code for, that's something I like to say is a significance, right? So now we got another vehicle here. What if we want to do the same test on this vehicle? Now this is a Chrysler. If we look at our wiring diagram a little bit closer here, we can see over on the left we have all the injectors in the coils. Look at this nonsense. All of them have a common power feed up on the top. And they go through the splice, which is this red circle, which picks up over here on this other diagram, goes here, we trace it. Where does it go? It goes into here, back traces all the way to the ASD or auto shutdown relay, which actually is fed both the solenoid side and the power output side of the relay by one fuse. However, the ASD relay operates a lot of components. So even if we put in a fuse tap here, we may not be able to pick out what's ignition and what's injection. And I will tell you that I have personally done this on some vehicles, and I've had very low success with the ability to see the distinct individual signals of current or voltage of any of these components because they are all on the same circuit. So what do we do in a situation like this? Again, this goes back to we need to remember we need to have an adaptive approach when we're using our scope. We need to understand that what works on this Ford might not work on this Chrysler. What works on this Chrysler might not work on this Volkswagen. So we always need to be prepared to make an adaptive approach. So in this case, what I would end up doing, generally speaking, is I would probably put my amp clamp around either side of the coil and look at what I got. As long as we're comparing apples to apples. So if I'm doing this coil here, I'm going to go either on this side or this side, or this side or this side. Now remember, the ground side is usually the side I like to look at, so that's probably what I would look at. Not so much if we're looking at current, but more so if we're looking at voltage. That's usually what I do. But again, just be consistent in your approach. So whether you're going to look at one or the other, just make sure you're consistent because you got to compare apples to apples. So now we're going to talk about how do we get the waveform on the screen. So this is really the part where we're going to do a little bit of a demo to show you how we get that waveform on the screen. So we're going to pause just for a moment here while I go over to the vehicle and we'll show you what we've got over at the vehicle. So now we're over at the vehicle and we're going to do secondary ignition as our initial demonstration of what's going on here. When we're doing secondary ignition on a vehicle with ignition wires, we need an inductive probe like this, which clamps on, and then we clamp it on to whichever cylinder wire we want to clamp onto to evaluate, and then there is a ground clamp like this, which you want to clamp onto somewhere good. Now, if you can reach battery negative, which actually I'm dumb because I didn't connect it to that, but battery negative is actually fully accessible on this particular vehicle, so we'll clamp onto battery negative. If you can't get to battery negative, you want to find somewhere good on the block that's a good spot to clamp onto. Now remember, the quality of your ground is going to affect the quality of your signal. So if you have a poor ground, your signal could be degraded, and you might form incorrect diagnostic conclusions. Now, the other thing to keep in mind about a battery, batteries are not just simply for supplying or acting as a reservoir for electrical energy, they also act as a dampener. So that's why the ground at the battery is a much better place to clamp on, right? So this is much healthier if we want to isolate our signal from false noise or noise that could be coming from poor ground quality at the block, from corrosion or something of that nature. Clamping directly to battery negative is ideal, right? Now, if you are evaluating some other circuit, like maybe an ignition, or excuse me, a camshaft signal or something of that nature, maybe you do want to go on the block, right? Because depending on where the ground comes from the camshaft, you might need to know okay, is the ground on the block any good? And if you don't know if the ground on the block is any good, you again could draw an incorrect diagnostic conclusion. So we're going to switch over to the scope screen now, and we're going to set this up. So I don't have the vehicle running yet, so you're going to have to bear with me here. I'm actually going to go on mute for just a moment so I can get that set up. So bear with me. All right, so you'll have to pardon me here. The noise might be a little bit on the loud side, but what we're going to do now is we're going to connect to the scope, and we're going to actually live demonstrate setting up a secondary ignition waveform. So I've got it plugged into channel 1, if I'm not mistaken. We're going to turn off all of our other channels here. I'm going to turn off of our rulers because we're not going to look at that. We're going to make sure that our sampling rate up here in the top right is set to 50/10M, which it is. And then what are we going to do? We're going to try to get the waveform on the screen. So I'm going to turn this off. So we're going to set our voltage scale. We're going to go over here. And we're going to say, hey, look, what kind of probe are we using? We're going to use the inductive probe. And the tool actually knows what it needs to set it up as. You can see it's setting it up as a 10kx. And it automatically alters all of the settings. I'm going to turn off this filter for now. And we're going to turn it on. And then we're going to click Run. And now we're going to put this time on the screen. So I actually have way too much time on the screen here right now. So we're going to put, go down to about 2 seconds on the screen. And we'll see if I have it connected correctly. And I think I don't. Naturally, I managed to break it, right? We'll give it a second here. I think I might have to reboot the app. Yep, so we're going to reboot the app here. So just pause for 1 moment. I'm going to back out, go into the scope, reboot the scope. So occasionally, you know, any tool out there can have issues like this. There we go. So now we got a signal coming on the screen, right? So we got 2 seconds of time on the screen. We've got our probe set up here. So we're going to look, and we got 10kx, we got DC, we got voltage set up. So now we're going to go ahead, and we're going to let it run for just a little bit here. I think we're going to press our tool here a little bit. Going to make the waveform a little bigger by toggling with the voltage range. So you see you switch it to 5 kV instead of 10. So now the waveform looks bigger on the screen. It's not actually changing anything about what the scope is capturing. It's just displaying it on a larger scale. So now you can also move your waveform up and down by touching the screen and dragging it up and down. It's kind of nice because it's interactive in that nature. So we'll get a few seconds on the screen, and we're going to press the stop button or run, and then we're going to hit zoom. And then we're going to play around with our time base and zoom in until we can see a waveform of ignition that we like to look at. There's one right there. Whoop, there we go. So now, we're seeing here that this is not the greatest of quality, right? So maybe we got a little bit too much time on the screen. So maybe what we do then, if we don't get the quality we're looking for, we're going to turn off zoom, we're going to change our time base, we'll change that to 500 milliseconds, right? So that's going to, the scope will be capturing more samples over a shorter period of time, right? That's what you're always limited by with your scope. If you want to capture tons of samples, you need to keep the duration. If you want your resolution or clarity of the signal to be really high, you got to keep your duration a little bit shorter. Now, you want to buy a $10,000 scope, then you can have both. You can have your cake and eat it too. If you don't buy a $10,000 scope, on the other hand, there's always a little bit of a drawback there, right? So now you can see the waveform moves a lot faster. We'll pause. Now we can zoom in. We're going to have greater clarity of waveform. So if we zoom in, we'll move it around here a little bit. There. Now we can see a little bit better. So now we can see there's a secondary ignition waveform right there, right? If I could actually drag this over a little bit. So there we can see what's actually happening, right? Now, if we turn on our low-pass filter, which remember, we turned that off. Let's turn on the low pass filter, see what happens. See how much the signal cleans up. Look at that, much cleaner. Now, we're going to stop it. We're going to zoom in. We're going to look at the time base here, and you don't have to use zoom. You can literally just use your time base manipulator like this. And we can take a look and we can zoom in. So now we're going, I want to get a little bit better amplitude out of this signal. I'm not real happy with this, right? So we're going to change it again. We're going to run. We're going to go 10 kV. We're going to go here. Get a little bit higher amplitude on the signal. We're going to change it to, we can play around with our low pass filter, jack it up, and then we'll hit run, stop. There we go. Look at that. Much better, right? We're going to zoom out a little bit. There we go. Now we can see a little bit better, more clarity there. So we'll stop it. See if we got a little bit. So we got a little bit, maybe not enough time on the screen now. So again, there's some playing around that you have to do to get what you want on the screen, right? That's normal for any scope user. So we're going to hit run. Now we can go back and we can review and find our scope. Find our capture. So we don't have what we want yet, right? Let's play around a little more. Let's add more time on the screen. Let's put 20 milliseconds on the screen. There, that looks better, right? So now we're going to zoom in. And look at that. We can see a little bit better there. Look at that. Now we can see our spark waveform, right? Well, that's a pretty terrible firing pattern right there. Now, this is a waste spark vehicle. So if we look at the screen up on the top where the zoom is, you notice how every other one of them, the amplitude of the signal looks a lot different. And so we need to keep in mind what kind of a system we're scoping, right? So we're going to move over here. If I can drag our window over, we'll look at this waveform because this looks a little bit more like a normal ignition waveform, if you will. All right, let's go. Wrong direction. All right. We'll zoom out a little bit so I can get it. There we go. There's a bigger one. And of course it zoomed off the screen. There we go. Look at this. These particular vehicles kind of have poor ignition quality, just to be completely honest. But if we're not getting a quality signal and we don't like what we're seeing, which I'm not super crazy about how this looks, right? This is not a great quality ignition waveform. This kind of looks like crap. So one thing you might want to do is let's check and see if our connections are all good, right? So we'll take a quick look here and we'll zoom out, put a little bit more, turn off our zoom, put a little bit more time on the screen. So we'll check and make sure our scope is clamped on nice. It's always a good operation. Maybe we're too close to the other wires. Maybe we've got interference here. We'll try clamping in a little bit different spot. So now we can hit the run button. We'll stop it. We'll zoom in. And now we can physically look at the waveform in a little bit more depth, right? Boy, the car really is kind of running like ass right now. We're not getting the greatest quality ignition waveforms out of this thing at the moment. So we'll see if we can go over here to this other one. A little bit more to the right. We'll go. There we go. That's a little closer. And that is one of the pitfalls of an older vehicle like this, right? This is a very, very, very imprecise vehicle. It is a very low quality, low precision vehicle. So our ignition waveform quality might be really poor. And I've actually done this a number of times on this vehicle, and it is usually kind of terrible. The other thing we might want to ask ourselves is, do we like the tool that we're using to look at this? Is this inductive clamp one that we're happy with? Maybe we want a different inductive clamp. Maybe this clamp isn't very good quality, or maybe we think it's marginal, right? So again, something to keep in mind when we're dealing with scopes is, again, we need to evaluate the quality of the accessories we're using and determine whether or not our connection or setup is adequate. But nonetheless, we are able to get the waveform on the screen and get some level of examination to happen, right? We can get some level of picture of, hey, what are we looking at here? So we'll zoom out again a little bit more here. There's another one that looks a little bit more like a regular waveform. That one's a little funky. So we'll go, anyway, nonetheless. So we got the secondary ignition waveform on the screen, right? So we can play around with the settings, so play around with your time base, play around with your voltage scale until you get something reasonably approximating what your waveform should look like. Using the Graham-Stokes book, we can get some kind of feel for what that would look like, right? So now we're going to go ahead and we're going to continue on to another test. Actually, we're going to go back to the slideshow first, so bear with me here. I'm going to switch to that. So we want to talk about a little bit, and I'm going to go kill the car here so it doesn't make so much noise. But we want to talk a little bit about when the scope is the right tool. So you need to understand when the scope is the right tool. And some of this is going to be practice, right? You're going to spend time on vehicles, and you're going to get comfortable with them and get more of a feel for when it's the right tool for your diagnostic process, right? Sometimes the scope is the only tool that's going to get you the answer. Sometimes it may not be the most efficient answer. On a great example one of my good friends talks about is, okay, we've got a misfire and we have a vehicle that happens to have coil on plug and it's a 4-cylinder and it takes 10 seconds to swap coils. Is it really more effective or efficient to scope it first? And the answer may be, no, it is not. So I'm not saying that there's no value in scoping it, because I think actually it's really good to scope it even if you don't use the scope necessarily to make the final call on a component. If you can scope something and get a waveform of a good versus a bad, you have a tool to communicate with your customers what is wrong with the vehicle, right? They have a visual demonstration of what is physically going on with the vehicle. And that looks like rocket science to the average consumer in many cases. And let's face it, it's real science. Using a scope is real science. This is what engineers do. This is what scientists in a lab do. Scopes are the most high-tech tool that you can use as an automotive diagnostic specialist. So I can't stress enough the value that the scope brings to you from a projecting and portraying your professionalism as a technician. If you learn how to use a scope and you can demonstrate, hey, this is before we fixed your car, this is after we fixed your car, the customer doesn't have to understand the nitty-gritty details of the waveform, right? They just need to understand this is before, this is after. It's just like an X-ray. Until you're taught what a bone looks like, you don't know. The doctor points at the thing and goes, here's the break, look at this. And you go, oh, I can see this squiggly line or whatever, and I can understand. That's broken, right? But that's the same thing with the scope. So once you can demonstrate or show that data, you can communicate much more volume in your diagnostic testing process and the value of your scope's or your shop's professionalism. So I think the scope is an excellent tool to convey your professionalism as a technician and also to show customers the value in what they're paying you for, right? That's very good. The other things you can do is you can capture intermittent problems with scopes. There are intermittent problems you can find with a scope you will never prove unless you use a scope. As a matter of fact, I host a roundtable event twice a month where technicians get together and we discuss diagnostic case studies. And there was a case study presented at our last event where the technician found the 2 cam sensor signals from each bank of the engine shorted together when the vehicle would go around a corner. Now, how on earth are you ever going to prove that unless you have a scope? And the answer is you're not, because the only way you can prove it is with a scope. Otherwise, you are doing nothing more than guessing. So, anyhow, something very important to keep in mind. Signal quality evaluation. Another thing there that's really important to keep in mind. When a car sets a fault code for, specifically, let's say, hey, we're setting a fault code for, let's say, cam sensor performance, right? We don't know why it's setting that fault code. But what can we do with a scope? We can connect to the power, the ground, and the signal. Again, we can do it at the component end and or the control unit end, and we can determine what is physically happening. Are we losing the signal? Is the signal amplitude insufficient? Is there power is dropping or ground is dropping? What's happening, right? That's the stuff we can see that we can't prove with other means. We can also prove failures or analyze failures with less disassembly. So we'll show a couple examples of each of these things I'm saying here. Also communication network analysis, because signal quality on a communication network matters as well. So here's an example. Now this isn't from a Topdon scope, but this is from another scope that works very similarly. So in this particular waveform here, we've got a cam sensor. And if we look at the cam sensor switches low, switches high, switches low, switches high, switches high, low, switches high, switches low, high, so on and so forth. And then right here, it gets stuck high. And we checked the power and the ground to the sensor, neither of which ever had any issues whatsoever. And we probed it at the ECM, and we could see that it would get stuck high because the sensor is not toggling low. And it would only be under heavy acceleration when the engine would get nice and hot. So electrically the sensor was failing. But we were only able to prove this because we could visually see it on a scope. Otherwise, that cam sensor fault code, if you put a cam sensor in that vehicle without seeing this waveform, you're guessing. You're not proving anything. And you can guess wrong. Because if you're playing the odds and you're guessing, it's not scientific, right? It's a guess. It's gambling. And lots of people like gambling for recreation, but I think we can all agree that customers are not going to appreciate you gambling with their wallet. Nor should you be gambling with the profitability of your shop or your integrity as a technician. So here's another example where a scope waveform is proof of a failure. This is a brake pedal position switch. So what does the switch do? The switch has power, ground, and then there's two poles of signal, which is what we have displayed here, and they are supposed to switch opposite. So the computer uses this to verify that the brake pedal position is a given position. So when one leg switches high, the other leg switches low. And it's supposed to mirror, each leg is supposed to mirror at all times. If it does not, that indicates there's an electrical problem inside the sensor. Because let's think about this, right? If it stays high on both, maybe it could be a power or a ground issue, right? Or stays low on both, it could be a power or a ground issue. If it doesn't, if we have an intermittent glitch like this on one leg only, what is happening here, right? Something else is happening. The sensor is shorting internally. The two poles are shorting together, or one pole is shorting to ground, or the other pole is shorting to ground or power. So, nonetheless, we can visually prove that this is a brake pedal position switch failure because we have a waveform that clearly demonstrates it. This is not something you can prove any other way. If you say you prove it some other way, you are bluffing. So, again, the scope, so valuable because of that. Again, this is something we could show to a customer. Hey, Mr. or Ms. Customer, if you look at this waveform over on the left, the switch is working normally. When you look over on the far right here, you can see the switch starts to fail right here. Whoops, we went backwards, sorry. We can see the switch starts to fail right here. So the customer doesn't have to fully understand other than good, bad, right? But again, this earns your value as a technician. This projects and portrays professionalism. This gives you better integrity when you make a diagnostic judgment call. So here are some of the tests that I would strongly recommend learning first. And again, these are tests where you can find YouTube videos on how to do them. You can take classes on how to do them. There are any number of options. So we've got relative compression with secondary ignition or primary, depending on what the vehicle has, if the coils are too insulated or not. Secondary ignition evaluation. So on many vehicles, now this vehicle's not great for it because the waveforms are kind of crappy because this just happens to be the way the system's set up, right? So some vehicles you can do secondary or primary ignition, and you can look at the waveform to determine whether a cylinder is lean or rich or properly combusting, right? So there's classes on that. Jim Morton taught a number of classes on this. I don't know if he's going to continue to teach them, but I think his class may be on YouTube as well. I would strongly recommend looking it up. I believe he calls it Sherlock Holmes Diagnostics, so definitely check that out. He does talk about secondary ignition in a lot of depth. Electric motors, that's another one we can actually verify operation of. So we're not going to get into depth on that, but there are classes on this as well. Injectors, we can look at current and voltage to see if the injector is physically moving. We can just make comparative analyses, right? We got a misfire on one cylinder, or we have a fuel injector circuit fault code on one cylinder. We have other good injectors on the vehicle, reasonably speaking, that we can compare to. So we can understand if there's a problem, right? Intake manifold vacuum. This is one you can use with relative compression test. Again, there's lots of videos how to perform this, and we will do a webinar on that specifically because it's a very valuable test to learn, but it will take more time than we can cover tonight. Communication networks, again, very important because you need to learn whether or not the quality of the signal is acceptable. Otherwise, you will have problems. And more vehicles have communication networks connecting more and more modules, so we need to be able to understand what is good and what is bad. So, this is a relative compression test with an ignition synchronization. So the ignition synchronization here on the bottom, we've got ignition sync right there. The ignition sync signal is on one cylinder. Again, this is a waste spark setup similar to this car. So every 4 humps is a cylinder. So we have basically here, this is a cylinder here, and then 2, 3, 4. I don't have the firing order in front of me, but essentially 1, 2, 3, 4. It doesn't fire in that order, but if it did, 1, 2, 3, 4, and then the cylinder fires again, right? So we can see by using the synchronization of the ignition waveform, we can look at a firing order diagram and we can determine which cylinder is which based on which wire we are clamped onto for which cylinder. So, very valuable test. This engine is healthy mechanically, and we'll go to a zoomed in view. You can see that our peaks of the relative compression humps right here, which are taken off of the starter wire or off the battery negative cable, depending on what's most accessible. We can see that the humps are symmetrical, right? That's what we're looking for. If we have a vehicle that has an uneven sounding cadence, or we've got a misfire on one cylinder, we can perform this test when the engine's cold, and we can perform the test again when the engine's hot. And then we can see whether or not the humps are symmetrical in shape. Symmetrical in shape tells us the engine has symmetrical functioning, right? Mechanically. That's what we're looking for. So again, we're not going to get into a ton of depth, just wanted to talk about it for a brief second. So here's an example of a communication network. This is a CAN network. Now this particular waveform is exceptionally clean. You will find a lot of them are not this clean. And again, I would encourage you to do some scoping of networks, even just for practice, so you can learn what is good. Find a vehicle with no problems, do some scoping. Best way to get comfortable with making more evaluative judgments. So now here's a secondary ignition waveform. This particular cylinder is lean. Now, how do we know that? Again, I know that because I've taken classes on this. So, again, we'll cover this in a class. Topdon will provide a class online. We'll do something in the future where we'll get into some of these tests a little bit more depth and talk a little bit more about the anatomy of the waveform. What does it mean? Things of that nature, right? And we're also going to cover just the specific circumstances where these tests make sense. So now, I'm going to try to give you at least a couple of live demos. Now, I can't make any promises that these are all going to go off without a hitch, but we're going to make an attempt here. So, we're going to do a live demo of a fuel injector current ramp. So, if you bear with me here, I got to open the garage door again so that I don't kill myself from asphyxiation, which I'm sure you can agree is probably a good plan. So, I'm just going to walk over and get my current clamp specifically for this. Now, my battery died on the camera here, so I'm not going to show you the clamp-on setup. But basically, we're just going to find one of the 2 wires at the injector, and we're going to clamp the probe on if I can access the wire specifically here. Well, we'll see if I can actually get it in there. We'll try. So we're going to go around the fuel injector wire here. And Volkswagen is exceedingly fun to get wires probed on, as you can well imagine. They are a boatload of fun sometimes. So actually what I'm going to do here is I have a knife that I have to use to cut the harness back. I have a little bit of a taping job on the harness here that is preventing me from getting the amp clamp around the wire. So we're going to cut the wire back a little bit here. And here's hoping I don't cut the wire, right? So, I'm going to get the clamp in here. And hopefully some of you don't mind if we go a little bit on the long side tonight, right? I do have a propensity to run long. That's definitely my jam, right? If you've watched me in any other trainings or seen me in any online stuff, I tend to go a little longer than I plan for most of the time, which, hey, you're just getting more value, right? So we'll try to get this in here. Oh, I almost got it. Come on, wire. There we go. Okay, so we got it around the connector. Now we'll see if we can get the connector plugged back in here. All right, so got the connector plugged back in. I'm going to go ahead and we're going to connect it to the scope. And just because things are simpler this way, we'll just connect it to channel 1, where we had the other connector set up. And we got to turn on our amp clamp. So a lot of amp clamps, if not all of them on the regular BNC style, have a battery. So they actually use a 9-volt battery. This is something you need to check regularly on your scope. If you do not, you are absolutely prone to incorrectly make evaluative judgments. So when I say that, there is always a risk that you will run into an issue with this if you do not use a new battery frequently. So you want to check your batteries really regularly. You want to make sure you're not having any problems with the batteries. 9-volt batteries seem to have a propensity to take a crap, so it's really important that you keep a big stock or supply of them on hand and make sure that you're replacing them regularly. Because again, this can cause issues with your amp clamp's performance. So we really want to be careful about that. And I think it's very important to check those regularly. I'm just trying to zero out my amp clamp here, so we're just about there. All right, so zeroing out the amp clamp a little bit. And then I am going to open the garage door because we want to make sure the garage door is open so I don't die. And then we're going to start up the vehicle here and see if we can get our waveform on the screen for the injector. Now this is a manifold injector. This is actually a very simplistic car. It's got a waste spark ignition system with 1 central coil and 4 coil plug wires. And it's got manifold injection only. So it is a very basic car. And it's actually good to start out on something real basic just to get comfortable, because a lot of the waveforms are very standard and generic looking. So we'll see if we can get it to run here. And of course I somehow managed to crash the app again, because I've just got the magic. I'm the magic guy today. Crash, 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 right? That's my middle name. Alright, so we're going to go back into the scope here. So back onto the scope. Alright, oh there we go. Hey, look at that. So I'm going to turn off zoom. We are going to we'll put a little bit more time on the screen here. We'll go 100 milliseconds. Make sure our amperage is set up correct. So I just arbitrarily picked. You can actually play around with your filter a little bit. Turn the filter up or down. I'm going to put it at 20 megahertz. And you can play around with this so you can see whatever your waveform looks like. So there we go. So we got a signal on there. We're going to change the amplitude a little bit. Whoops, I went the wrong direction. Alright, so we're going to go ahead and we're going to stop it. And now we're going to zoom in. Alright. And I might be on the wrong wire of the injector here, and it's kind of looking that way. I didn't bother to look which wire I was on, so shame on me, right? You got to look at your wiring diagrams. Yeah, we're looking like we're on the wrong wire here, so bear with me. Maybe we can zoom in a little more there. I am not happy with that, so I'm going to switch to the other wire here. If I can without making the car stall, right? Alright, so hooked up to the other wire now. See if our waveform is a little bit better there. Alright, run. Nope. This is how you learn, right? Set it up one way, set it up the other way. Find out, did you do it right or did you do it wrong? So we'll do 10 milliseconds. Aha! There we go. Dummy just had it on the wrong scale. So here we go. We'll get a little bit more time on the screen here. We'll freeze it. I'm going to zoom in. All right, come on, you. There we go. And I think I'm inverted here, potentially. No. Nope. All right. We're going to go zoom. We're going to take a look at a couple of different waveforms so we can get one that we like. So we're going to zoom in. We'll zoom out till we find a spot that we like on the waveform here. So again, you can see there's a lot of playing around that you got to do until you get what you want on the screen. It's not all exact science. You'd like it to be, but it's not. You can see an injector firing right there. And it almost looks like it's firing twice, if I'm not mistaken here, right? So kind of an interesting waveform. And these old vehicles, man, oh man, I tell you, manifold injectors, they are slow and they are absolutely imprecise, which is why most vehicles cannot use them anymore as their primary mode of fuel delivery, because you don't get the same level of atomization or precision that you do with a direct injector. We'll find one more waveform here and we'll look and zoom in a little bit more. There, that looks better. Look at that one. Again, we get pretty terrible quality waveforms on this Volkswagen. But again, what we're really focused on here is not just, hey, we can get the waveform on the screen, but we would want to make a comparative analysis, right? We would want to look at multiple cylinders. Hey, what does this cylinder look like? What does that cylinder look like? Are we seeing symmetry between the cylinders? That's what we're looking for. And again, we're going to find out, does it match a symptom we're chasing or does it not, right? That's what really matters about it. So now what we're going to do is I'm actually going to switch back to the slideshow and we are going to do a window motor. So I'm going to turn the vehicle off and show you what that looks like. Now this is a really interesting test, and I learned this from a gentleman named Hans Jorgensen. And Hans is an awesome guy. He actually teaches at a college now. And Hans taught me that if you have any kind of actuator on a vehicle, window motor, etc., and you want to look at what it's doing, and maybe it doesn't have a dedicated fuse, you can go around the battery negative wire and you can manipulate just that device. If you can get everything else turned off and you can manipulate just that device, you can verify the condition of that. And think about it. You have 4 window motors on a car. If you have one that's not functioning correctly, we could scope all 4 wires and get a good feeling for what's going on with that particular one motor, right? Now, I'm going to attempt to clamp around the battery negative cable here. So bear with me for a second. I think I can get my amp clamp around that. Yes, I can. All right, so go back into the scope here. I'm going to relaunch it. And we will go to the scope. And look at that. There's something happening on there right now. I'm going to turn off zoom. So really right now, this is literally the battery negative cable right now. So something is happening on that circuit. I don't know what. Obviously, everything goes back to the battery negative cable, so we're not going to worry too much about that. But what I want you to watch is I want you to see what happens when I actuate the window motor. I'm going to put a ton of time on the screen here so that we can actually get a fair amount of signal captured. So we're going to put like 20 seconds, 20 seconds on the screen. So I'm going to go over here, I'm going to work the window motor once. And I want you to watch and see what happens when I go up and when I go down. So we'll go up first. It's all the way down right now. Up. Now we're going to go down. Down. Right? So you can see that on the scope. So we'll stop it here and we'll zoom in so you can see what's happening, right? So I'm going to go all the way over. We're going to zoom in and we can physically look at what happens with the current. So we can see, look, it goes up there when I first go to move it. And then it goes up again when I first go to move it the other direction, right? Initial movement. So now, here's another thing we can do. What if we want to know if it's binding? I'm going to simulate a binding condition by simply putting my hand on the window. So I'm going to hold the window as I try to move it up. Watch what happens with the current. And then I release it. See that big giant spike? That's mechanical binding right there. That's me pushing back and providing resistive force to the window mechanically. So we're going to pause it here, and then we're going to zoom in. So you can physically see. Get into our window here, and we're going to zoom in. Whoops. Okay, so we're going to go here, and we'll zoom in a little bit more. Look at that. So there's your mechanical binding right there. See how the current continues to go up? So the initial spike of it moving, and then I push on it and the current stays higher for longer, right? Because it's mechanically binding and it's being stopped from moving like it's supposed to. So again, there's any number of things that we can see when we are looking at the window motors. I'll run the other window motor once now. We're going to leave the driver's window, which is the one I was playing around with. We're going to switch it back to run. And now I want you to watch, we're going to run the passenger window all the way down and all the way back up. Automated. So there's auto roll down all the way. Okay, the window's all the way down. Now we're going to let it go all the way auto up. And you see that spike that happens? The spike is what's telling the control unit, the driver's door control unit, hey, it's reached its end stop, turn off the motor. That's how those automatic window functions like auto up and auto down work, which is one of the reasons why you have to relearn them, because it needs to see that spike so that it knows to shut the circuit off. So again, these are things that you can learn from classes, right? More stuff that there's all sorts of training available on. But it's really interesting to dive in and look at this stuff in more depth, right? So we can see where the window started moving, right there, the big tall spike. Then we can see it moving, and then it goes all the way down, and then we hit a spike when it stops, right? So again, multiple times we can see what's physically happening reflected through current, and we're literally just at battery negative right now. So I thought we were going to have time to scope a CAN network. We're not going to have time to do it this time. However, I can promise you we will do a webinar on networks. We will do a scope webinar on networks. We'll do LIN bus, we'll do CAN bus. If I can get a vehicle with FlexRay, we'll do that as well. However, like I said, I greatly apologize, but we're not going to have time to do the CAN network tonight. So, please, if you have questions, let us know. Post on the official Facebook page, post it to YouTube, hit us up, hit us at support, shoot us an email, and get at us any way you can. You can certainly let us know in any way, shape, or form. So we do have some questions that are coming in here that I am going to answer. So let's see what we got here. So the first question is, if you use presets, will it change the user set to a lower sampling rate? I don't honestly know, because I have not played around with the automated settings before. But that is an interesting consideration, and I would strongly recommend that you double check that. So that's a great question, and like I said, I don't know the answer because I haven't tried it. I never use the automated settings. I always use manual. It's just the way that I've always used the scope, right? So I haven't played around with the automatics. However, I would strongly recommend that you verify that the sampling rate has not changed. Now you can see the sampling rate up in the top right of the screen there. We can actually see the sampling rate. You see how it says 50M, 250 KSAS? So that's kilosamples a second. So that is somewhere where you can monitor and see what it's physically doing. And it is something that will change dynamically. So again, some of that's limited based on how much time you have on the screen and whatnot. But again, it's really important. I would say that question's great because again, it's something you want to double check just to verify, right? And then the other question was, what is the name of the electrical book? The name of the book is so the electrical book is How to Diagnose and Repair Automotive Electrical Systems. The author is Tracy Martin. I think Tracy Martin's a guy, but I don't honestly know. And then the name of the automotive oscilloscope book I recommended is Automotive Oscilloscopes, Waveform Analysis by Graham Stokes. And that's spelled Grahamstoakes. And like I said, both of those books are fantastic. I would highly recommend investing in both. And again, I would super strongly recommend take every electrical class you can take every scope class you can take. You will always get better. You will always learn more information. And there's no limit to how much you can improve yourself if you take the time to go through training. And again, please watch our YouTube channel and take note of that. We're going to continue to provide trainings as much as we possibly can. We'll try to do some more webinars. I'll try to do some more live car stuff like we did tonight. We'll try to do additional things like this just to give you a little bit better feel, right? Now, if there's specific components you really would like us to talk about or scope, we'll do our best to accommodate that. So, don't hesitate to hit us up if you've got ideas or thoughts. We're happy to try and do that if necessary. So I'm just checking the question queue to see if there's anything else. Pause for just a moment here. We're going to go back to the slideshow here. So, got a couple other things to show you that I did want to talk about, even though we didn't get to scope a network. There is one thing I would like you to keep in mind on scoping networks, just a quick tip. So when you're scoping a network, it is really important where you are connecting to the network. So this wiring diagram is just a physical demonstration that if you're going to scope a network, you need to know if you're actually talking to the network where the modules are talking to each other, or only where the scan tool talks to the gateway. So in this wiring diagram in the red square, basically this is a CAN line twin pair, so two CAN lines, a high and a low, that are going from the data link connector to the gateway module, which is J533 on this Volkswagen. So if you put your scope on those two wires and you do not have a scan tool connected, you will not see anything happening on this particular communication line. The other thing you want to keep in mind is if you are scoping this line and you are trying to verify the integrity of the network, it's meaningless, right? Because the only thing that lives on these two lines is the DLC where the scan tool connects and the gateway. So you're not evaluating what's going on with the vehicle's network by connecting here. Instead, you want, and this would be if you're going to connect to the breakout, the OBD port, you're going to use a breakout box like this. That's the best way to go. But what we'd really want to do is we want to access that gateway module and we want to connect our scope to the specific wires for each section of the CAN network. So the CAN network is often split up into partitions. Certain modules will live on certain partitions, and depending on what your fault codes are, you will need to follow those fault codes, and you will need to follow and figure out which network they're talking about, and you'll want to connect your scope to the network leg where that module resides and where that fault code originates from. So, a couple other training resources I just want to recommend. CTI and WTI, CarQuest Technical Institute, CTI online, and WorldPack Training Institute, also online. They provide a number of scope-related webinars. You can see I just did a search on their website recently. You can see we've got electrical troubleshooting with a scope. We've got another one that's set up in operation, and then we've also got engine technology and then condition testing with a scope, basically. So tons of classes available like that. Some are paid, some are free. They do webinars, and again, we're going to do webinars here for Topdon as well. And Master Automotive Training, if you're listening and you would like training in Spanish, Master Automotive Training does a lot of training in Spanish. They also do use a scope that has a very similar user interface. So if you have a Topdon scope and you need training in Spanish, look at Master Automotive. They have a bunch of training with the MixSig scope, and the user interface is extremely similar to our Topdon scope. So if you already have our scope, you can still get training that will make sense to you, even if you watch their training as well. So just wanted to share those other training resources. And then the last thing I wanted to share was how are you going to analyze your waveforms successfully, right? That's something we talked about earlier in the class here. But the one thing I want to recommend is there's 2 dedicated Facebook groups. I've put the links in here, and you can contact us if you need these URLs, or you can pause the video and obviously write them down. However, These are groups that you can join publicly. You can post waveforms. You can get assistance from other technicians. You can get instructor assistance. There are many instructors in these groups who will reach out and help you. And you can learn because other people will share waveforms and show you examples of things that maybe you're not familiar with. I would recommend you attend as many classes as you can about the anatomy of a waveform for various components. Get comfortable, take as many electrical classes as you can, and remember, you have symmetrical components on a ton of vehicles that will allow you to have a known good on the same vehicle that you have a faulty component, right? Just like we did with the window motors. If we had one that was faulty, we could compare what the waveform looks like to the one that's not faulty. And we can observe what does the normal function look like, and then we can observe what does the abnormal function look like. And then, if we've had sufficient training, we'll understand what the waveform means. But I would strongly recommend scoping known good vehicles that are not broken, because this will get you more comfortable with what a normal waveform for a given component looks like. Again, this is a great way to sharpen your skills and get much more comfortable with your scope, so I would strongly recommend doing that for sure. And again, if you got other questions or you have ideas for what you'd like to see us cover in future webinars, again, don't hesitate to reach out. You can post it on the Facebook page. You can reach out directly to us via social media. I'm on social media and I'm very easy to find, so please don't hesitate. We're very happy to help if we can. So that concludes our webinar for tonight. Greatly appreciate you coming to watch. Again, I'm Haakan, and thanks for purchasing a Topdon tool. We really appreciate your business. If you spent time using the Macs and you like it, we'd love to hear that. If you got feedback on ways we can improve in the future, we're always interested in that. Greatly appreciate you purchasing the tool and using it every day. And again, any way we can teach you more things to help you do that more effectively, we're open to those suggestions all the time. So again, thanks again for watching.